Hello, my lovely friends. This is the video for the lesson 7 on pointers when we're looking at C programming. I know in the past I've said don't worry about this, but guess what? It's time to worry about it. A lot of connections are going to be made here with things that we've done in the past, and hopefully they'll make a little bit more sense to you. We're going to be covering the very first part of Chapter 7 and then 7.8 in our book, How to Program, with an introduction to C++. So pointer introduction. The pointer is one of the most powerful features that C has. Okay, a pointer is going to allow a program to do the pass by reference that we spoke about last lecture in the arrays for any type of data or data structure. It's going to allow you to pass functions between functions. It's going to allow you to manipulate strings and arrays, which we're going to look at in the next lecture. And it's going to allow you to create and manipulate dynamic data structures that are going to be able to grow and shrink at execution time. Remember, we talked about arrays, and with that array, you need to know how many elements are in it. Well, with this addition of the pointer, we can create items that can grow and shrink on the fly. We're not going to get into that in this class, but you will in your algorithms and data structures class. A pointer is treated the same as any other variable. You need to do the same 3 things that we've done since class 1 with variables. You're going to have to declare, initialize, then use in that order. A pointer is nothing more than an address to a memory location which contains a value. Okay, so it's called a pointer because it points to the memory location for the variable. A variable is said to directly reference a value. So here I've got a variable count. Count is 7. It's direct. A pointer, on the other hand, is going to indirectly reference a value. So my pointer is going to point to a memory location, and inside that memory location is the value of 7. So it's indirectly getting you to the same location. When I reference a value through a pointer, we call that indirection. It's indirectly referenced. Remember, step 1, we declare. So what we do is, in order to declare a pointer, we have to declare what type of variable it is pointing to. So in this case, it's pointing to an int, and we give it a name. The biggest difference is this asterisk right here. That is going to indicate that I am talking about a pointer and not just a variable. So the way I read this is I'm actually going to read it right to left. So count pointer is a pointer to an int. Using good programming techniques, if it is a pointer, we usually use some sort of indicator in the variable name to say that it's a pointer and not just a typical variable. So we might use things like a capital PTR after a variable descriptor, or we might do something like start it with a P, like down here at the bottom, P count. So both of them are good ways to do it. Now I will say, while you're writing a program, pick one or the other of these two and don't go back and forth between them, but stay consistent within that program. When we define a pointer, we use that asterisk. Now, when we put the asterisk, it is only going to apply to the variable that it is directly beforehand. So here I've got int, and I've got a pointer, count pointer, and I've got a regular integer variable of count. This asterisk does not distribute in any way, shape, or form. It is just going to be connected to that variable name that it is directly in front of. In order to prevent confusion, we can actually go ahead and write this on as many lines as we want. Remember, the compiler and the program and the computer, they don't care. But In order to remove that ambiguity in the human brain, it's easier sometimes if we just put all our pointers on one line and all of our traditional non-pointer variables on a second. The next thing we have to do is we have to initialize it, which means we have to give it an initial value. Now, initialize pointers when they're defined, or we can assign them a value. This is very similar to what we did with the variables. Now we can also assign it to null. Null is nothing, okay? So a nothing address is going to point to a nothing memory location. Now a 0 is going to be the same as a null, but since 0 could actually be a location, we prefer null as programmers. So we've indicated how we say to the compiler that the variable is a pointer, but how do we get what's inside the pointer? Well, we use something that we call the address operator, or the ampersand sign. That is going to return the address of what's in there. Here I've got an integer variable y equal to 5, and we've said in the past that what that does is it goes and it allocates a memory location and places the 5 in it and calls it y. That's what we have going on over here on the right. Now, if I were to declare a pointer, y pointer, which is going to point to an integer, okay, this is what we did in the previous slide. I can assign it a value by saying it is equal to the address of y. What that is going to do is it's going to create this y pointer, and it is going to point to the address of the location of where y is. So that's initializing the pointer with y's address. Now we can casually say that y pointer is pointing to y. So for example, y may have an address of 600,000 with a value of y. Well, y pointer is going to have the value of that address of 600,000, even though its location is at address 500,000. We also call the asterisk the indirection operator. Remember, it indirectly references something, but it's also called a dereferencing operator. Now, your asterisk and your ampersand are going to be opposites, okay? So, apply to a pointer to get the value of the object. So remember, the ampersand sign is going to be your address, and then your asterisk is going to be your value. When we use that asterisk, we're saying that we are dereferencing a pointer because your pointer is a reference. So in order to dereference it, we get the value. Here we've just got a printf that we've done before, but what do we have here? We have an asterisk and y pointer. That is going to print what is the value of whatever is in y pointer. If we try to dereference something that hasn't been assigned or doesn't have an address, that's going to be an error, and it could actually be quite harmful to the stability and the security and the structure of your code. So please be careful to make sure you have an initial value before you try to dereference it. There's a lot of code in here, so go ahead and either download the handouts or you can pause the video in order to write this down. But I'm just going to take out those lines that we really want to use. We have something called a conversion specification, okay? And that's going to output your memory as a hexadecimal, okay? Remember, your ampersand and your asterisk are complements of each other. One's going to give you the address, one's going to give you the value. So in this example, lines 5 and 6, I have a variable a, and I have a pointer assigned to the address of a. Now if I print the address of a, and I give it the ampersand a, that's going to print out the address in a hexadecimal. The value of a pointer is going to be that same address value. Okay, so you can actually use those ampersands on regular variables, kind of like we did with the scanf. It looks quite familiar, doesn't it? The next thing we're going to do, value of A, and we're just going to print A. So the value of that variable is 7, because that's what we said on line 5. And the value of star, remember the asterisk or the star gives us the value, is also going to be 7, because we dereferenced that address and got the value. Here we're showing that star and asterisk are complements of each other. So here we're going to do two crazy things. We're going to do an ampersand star and then a star ampersand. Well, they're both going to give you the same value. They're both going to give you the address. So the order in that doesn't matter, but it will give you the address every time. Now, when you're printing out these addresses, just like we did with the arrays, those address numbers and values are going to change between computers and even between the same computer if you run it at different times. Remember, those memory addresses can change. Here we've got a chunk of code that is going to pass by value. Remember, passing by value is a copy. So this is nothing different than what we did before. This is just going to be a refresher. So number on line 10 here, number equals cube by value, I send it number. So here it sends an int, which is a copy, right? And it returns n times n times n. So if I send it 5, it's going to return 5 times 5 times 5, or 125. So the new value of number is going to be 125. So here the original value is 5 from line 9, and then the new value is 125 from line 11. Now, one thing we can do with these pointers is we can pass by reference. So it is kind of a cool thing to do. Passing by reference, if you remember when we talked about arrays, passes the actual variable memory location. So anything you do within the function will be changed by the calling function. That's pass by reference, because you're passing the address location and then you manipulate the actual address location. So no copies are made. So here I've got the original number is going to be 5, which is what we had before. Now, on line 11, you can see one of the differences, I don't have number equals anymore. I just call cube by reference. Now, the biggest thing that is different here is that I send it the address of number. When that function receives it, the big difference here is I now have an asterisk and I'm saying that it is a pointer to an integer. When I do the manipulation, there is no more return. I'm not returning anything back because I am manipulating the value of the actual pointer. So in that actual memory location, I want to take the value, multiply it by the value, and then multiply it by the value again. These are the multipliers. The ones with the variable name are the dereferencing. So I get 5 times 5 times 5 times 125. Well, the new value when I print it up here on 12 is now going to be 125 because I manipulated the actual memory location, so it manipulated the actual variable. Oh, I don't know what's going on with this. We're skipping this. There we go. So functions that receive one-dimensional arrays, we talked about arrays last time. So the compiler is not going to distinguish between a pointer and a one-dimensional array. Because remember, a one-dimensional array, that array name points to the memory location of the value in index 0. So the function is going to have to know when it's receiving an array versus a single variable. Because remember, they're both passed by reference. So it looks the same from the computer's point of view. Int array B can be converted into int, pointer to b. These two forms are interchangeable. Okay, we kind of talked a little bit about that when we talked about arrays. But now, hopefully, we're making some of those connections to why the array looks and acts the way it does. So, here is what is happening in your memory when you pass by reference, okay? Let's look at value first. So, for value, here's my main int number 5. I create a memory location. I give it the name number. I put the value 5. Now I'm going to do number equals cube by value. Well, what that's going to do is it's going to go and call the function cube by value. Here it's going to create another integer n with a separate memory location to use within that function. And it's going to return n times n times n, which is the 125, which is what we looked at just a minute ago. It's going to do that calculation and it's going to be stored in n here. Okay? That number is then replaced by this function call, and the number is then set equal to 125. So the memory location for the original is then sent to 125. Now let's take a look at what it looks like if I pass by a reference. So here, step 1 is identical to the pass by value that we just did. We create a memory location, call it number, put in the value of 5. Now, step 2, we're going to call this cube by reference. We're sending it the address location. So when we come into the function, we have the address location of the original. So my n pointer is calling this original memory location. Then we're going to do that n pointer equals n pointer times n pointer times n pointer. So it's going to take the value in here, which was the 5, and do 5 times 5 times 5, which is 125. It puts it into that location. So into that location goes the new value of 125. There's nothing else that has to be done in order to recall this actual memory location. It's just there. Now, pointer expressions and pointer arithmetic, you can do some arithmetic and assignment and comparison, but they're not all going to be the same as when we do traditional math, and you can't use all of them with pointer variables. So some things we can do and that are allowed is we can increment or decrement, so add 1 or subtract 1. We can add an integer, we can subtract an integer. We can actually subtract one pointer from another, okay? But both pointers need to be in the same array. Now, any type of arithmetic on pointers that don't refer to elements, it's going to give you an error, but it's not going to know that until it's runtime. So it's going to be a logic error. And again, it's going to be that array index out of bounds. So aiming a pointer at an array. So now we're combining our understanding of the pointer variable with our understanding of arrays. So let's assume V is defined and the first element location is at memory location 3000. So up here we've got memory, and then here we've got the indices and the variable name. Assume that V pointer is going to point to the very head of this array, so it's going to have the value of that 3000. Okay. So we can initialize it in two different ways. We can either say V pointer equals V, because remember, that variable V points to the very head of that array. Or we can say that V pointer is equal to the address of the first element. They both mean the same. I said we can add an integer, but it's a little different than when we do it in math. So in arithmetic, 3000 plus 2 is going to give us 3002. That's not how we do math when we talk about a pointer. Okay, so When we add an integer or subtract an integer to a pointer, it is going to move that many elements, which may or may not necessarily be the same as our arithmetic. So for example, let's take our v that we just talked about. If I add 2 to v, if I'm originally at 0 and I add 2, I go to 1 and I go to 2. Okay, so instead of being at 3002, I'm actually at 3008 because I moved one element, I moved 2 elements. I did not add 2 to the actual memory location. That would put me at 3002, which would be somewhere in the middle of the first element. So that's not how we add when we talk about pointers. The same goes for subtraction. So here I can say if my pointer is pointing to here at 16 originally, and I want to subtract 4, it's going to go 1, 2, 3, 4. And then this is going to point to right here at the head. Again, it's going to jump that many elements and not subtract 4 from the address. You need to be very careful when you do pointer arithmetic because your pointer could be out of bounds. You get that array index out of bounds, which is a logic error because it's not found until runtime. That also can lead to those same problems we talked about before when we talked about pointers with structure stability and security. So just be very careful that you do enough checks and balances that your array is not going outside of what you have. So for example, if I tried to subtract 6, I can only subtract 4 because if I subtract 6, I'm out here 5, 6, and I don't know where I'm at. Okay, so again, that's going to give you an error. I can use the increment and the decrement that we talked about before, so I can increase by 1 and decrease by 1. But again, it's going to increase and decrease one element, not the value of the address. I can subtract 2 pointers from each other as long as those pointers are in the same array. Okay, it's going to be the number of array elements between those pointers. So if I have my first pointer at 3000, my second one at 3008, it's not going to be 8. 3008 minus 3000. It's not what's going to happen. What's going to happen is I'm going to look at here and say I've got this one at 3008 and I've got this one at 3000. There are 2 elements between those 2 numbers. So it's going to give me the value of 2. So remember that pointer arithmetic is always going to be based on elements. And we need to make sure that we stay within the array when we do any of this manipulation. We cannot go between arrays. We can assign one pointer to another as long as they are of the same basic primitive data type. So there is an exception. There's an exception to every rule. Pointer to a void. Okay? A pointer to a void is generic. It can point to any kind of type. So if we want to point between integers and characters, go ahead and use void and as your data type, and it will point to anything. But again, this is a little bit dangerous, so make sure that when you're doing this, it's actually needed, and then there's just not a better way to do it. The pointer to the void cannot be dereferenced. Okay, it contains unknown type. Okay, so it doesn't know how many bytes there are. You're going to have an issue with you can't do the arithmetic. And you also can't dereference it, and it's going to be a syntax error. In order to do any of that arithmetic and to dereference it, your compiler has got to know what's in there. With a void, it doesn't. So again, you're opening up to a bunch of different errors, and this one will explicitly give you a syntax. So that will be at compile time, so it's a little easier to find. We can compare using our equality and relational. Okay, it's only meaningful, again, if we're in the same array. Otherwise, it's going to be a logic error, so that's runtime, harder to find. Most of the time when we use some kind of comparison is if we're determining if a pointer is a null or if there's an actual value. Now, when we look at pointers and arrays, there are relationships between the two. A lot of times we can use them interchangeably. So that array name is basically a constant pointer. Remember, we talked about that it's actually indicating the first element location. So these two expressions actually mean the same thing. Okay, the array name B is a pointer to the first element. You can set B pointer to just B, and they're both equal to the address now. We can also say B pointer is equal to the address at index 0. They mean the same thing. Today we covered a little bit about pointers, and we made some connections between pointers and arrays, and hopefully that will clear up some confusion, and it'll get you a little bit more understanding when we talk about those pointers and that array and the dereferencing and the referencing of values. The assignments that we have going forward is homework 6, which is about pointers, homework 7, which is strings, lab 8, which is another debugging lab. It's going to be shorter than last time. No pointers or strings from this week. 9 is going to be pointers, 10 will be strings. Next week, we are going to talk about input and output and structures and unions, but the next video will be talking about working with strings. So I hope you've enjoyed this, and it's been a lot of information. As always, contact me with any questions, comments, or concerns. Hope you have a great day.